Hello and welcome to Mystery Science. Today we're going to be looking at CC9b, conservation of mass. This slots into the CC9 chemical calculations part of the Edexcel combined science course. Now, I've left a little bit out of this today. Normally when I'm teaching this, I will pause and I will teach balancing equations. I started doing this and I realized that this video would be far too long if I added that in there. And so I've decided to take that bit out and I will be doing a separate video about balancing equations because it really needs its own time and its own space. So look out for that coming very, very soon. So this lesson, we're going to focus on the conservation of mass, both as a law and as a means for calculating the mass of the reactant or a product when you know the mass of the other. So if you know the mass of the reactant, you can calculate the mass of the product, and vice versa. If you know the mass of this thing, the product that you're making, you can calculate the mass of the reactant needed for it. Before that, let's do a little do now recap and let's have a look at finding the empirical formula for a compound which contains 40% sulfur and 60% oxygen, a compound which contains 37.21% carbon, 7.75% hydrogen and 55.04% chlorine. Hold up a minute, Mr. E. In your last video, you didn't talk about percentages, you talked about mass. It doesn't matter, you do exactly the same thing. You still get matter, grrr, but instead of where you write the mass, you're going to write the percentage. And when you calculate or do the division, you're just going to use the percentage divided by the relative atomic mass, just like you did before where you had a mass in grams, but now you're going to use a percentage. So pause the video, have a go at those, and then come back. Okay, so in our first question, we have a compound which contains 40% sulfur and 60% oxygen. Now, those percentages add up to 100, so we know we're only really looking for something that has sulfur and oxygen in it. We write down the relative atomic masses. So for sulfur, it's 32, and oxygen, it's 16. Then we simply divide the percentage by the relative atomic mass. 40 divided by 32 gives me 1.25. And I do the same thing with oxygen. 60% divided by 16 gives me 3.75. Now, I divide both of those by the smallest number. So 1.25 divided by 1.25 gives me 1. 3.75 divided by 1.25 gives me 3. So my ratio is 1 sulfur to 3 oxygen. So my empirical formula is SO3. Okay, so in this example, we're giving a lot of elements and we're giving a whole bunch of different percentages, and it looks really confusing, but you do exactly the same thing. And if you struggled with either of these two, then go back and watch my previous video, CC9a, where I teach you exactly how to do this. So we start with our carbon. It tells us we have 37.21% carbon. The relative atomic mass of carbon is 12, so we do 37.21 divided by 12, which gives us 3.1. Hydrogen, we do exactly the same. We're told we have 7.75% hydrogen. So we have the relative atomic mass of hydrogen, which is 1, and that gives us 7.75 divided by 1, which of course is just 7.75. Chlorine then, we're told we have a whopping 55.04% of chlorine, and the relative atomic mass of chlorine is 35.5. So you divide the percentage by the relative atomic mass, 55.04 divided by 35.5 gives me 1.55. So the smallest number from these three is 1.55. So if I divide 3.1 by 1.55, I get 2. If I divide 7.75 by 1.55, I end up with 5. And of course, 1.55 divided by 1.55 is 1. So my ratio is for every 2 carbons, I have 5 hydrogens and 1 chlorine. So my empirical formula is C2H5Cl. Okay, so nestled inside this conservation of mass module, we've also got a little bit of a recap about solutions. So what is a solution? Well, a solution is where you take a solvent, put a solute in it, and you end up with a solution. So it is a dissolved mixture of the solute inside the solution. So the solute has completely dissolved. It's dissociated and dissolved into the solvent. So when a solute is dissolved in a solvent, you end up with a solution. Okay, so let's have a quick look at concentration. So here are 2 beakers. They both have exactly the same volume of liquid in. But in the first beaker, we've got a low amount of solute. So this is a very dilute, a weak solution. Whereas in the other one, I've got lots of solute in there. So that makes a stronger, more concentrated solution. Think about squash or cordial. If you put a little drip inside a volume of water, you're going to end up with some kind of weak, nasty, barely flavored drink. Whereas if you put loads in there, you're going to end up with a highly sugared beverage. So that's the difference between dilute and concentrated. Dilute solution doesn't have much solute in it. Concentrated solution has a lot of solute in it in the same volume. So the higher number of atoms or molecules that are in the solution, we say is the more concentrated solution. So in a concentrated solution, we have a higher number of atoms or molecules than in the dilute one. Of course, this wouldn't be a chemistry calculations lesson without doing some calculations. So let's look at how to calculate concentration. Now, notice that we use some very strange units here. We're using grams per decimeter cubed. So a decimeter is 10 centimeters, and a decimeter cubed as a volume is the same as 1 liter. So let's have a look at the equation that we use. The concentration in grams per decimeter cubed is the mass of the solute in grams divided by the volume of the solution in decimeters cubed. So this is an equation with 3 terms, and it's one that we can use an equation triangle for. And make sure that you know the units. So the mass of the solute, which we use N for instead of mass because it's small, is in grams, C for concentration, and V for volume. That's chemists for you. So this is very, very important. 1 decimeter cubed is the same as 1 liter. That's 1,000 milliliters or 1,000 centimeters cubed. 1 centimeter cubed is the same as a milliliter. Whenever you get a question, they like to put weird volumes in. But we say weird, but volumes that you or I will know. For example, 25 milliliters or 25 centimeters cubed. That, after all, is what's on our measuring cylinders. So we have to convert our units. If you're given units in milliliters or centimeters cubed, you have to divide by 1,000, and that will give you your units in decimeters cubed. So let's say, for example, they say you have 25 milliliters of water. To calculate that into decimeters cubed, you divide your 25 by 1,000 and you end up with 0.0025 decimeters cubed. simples. I think I missed some noughts there. Sorry. Okay, so here we go. Here is a worked example. So what I'd like you to do is pause the video and have a go at this. So what is the concentration of a solution that's got 36.5 grams of solute in 500 centimeters cubed of solution? See, centimeters cubed. Tricksy. So we remember our equation triangle where N is mass, C is concentration, and V is volume. So the volume of the solution in decimeters cubed, because remember we have to convert, it's going to be 500 divided by 1,000 to get our volume in decimeters cubed. So that's nice and easy. That's 0.5 decimeters cubed. So now we just plug things in the equation. Concentration in grams per decimeters cubed is 36.5 divided by 500 centimeters cubed. There we go. So we're doing our SRAO. We have written the equation. Concentration is equal to mass divided by volume. So we've substituted our numbers. We don't need to rearrange because our subject is the unknown. And so we calculate the answer, and we have the answer of 73 grams per decimeter cubed. Okay then, pause the video and have a go at these three. Now these three challenges do get progressively easier. So if we look at the first one then, 20 grams of sodium chloride, that's table salt, is dissolved in 2 decimeters cubed of solution. That's 2 litres. So 20 grams divided by 2 decimeters cubed, because it's already in decimeters cubed, it gives you an answer of 10 grams per decimeters cubed. Well, what about the next one then? 9 grams of copper sulfate is dissolved in 1,500 centimeters cubed of water. Calculate the concentration. Well, first thing to notice is that our units are not in decimeter cubed. So we have to divide our volume by 1,000 to get it into decimeters cubed. So 1,500 divided by 1,000 gives me 1.5. So 9 grams of copper divided by 1.5 decimeters cubed gives me a concentration of 6 grams per decimeter cubed. Okay, so our last challenge then, we're going to have to do some rearranging here. It says calculate the mass of glucose in 500 centimeters cubed of 6 grams per decimeter cubed glucose solution. Well, the first thing to notice, of course, is that 500 centimeters cubed needs converting into decimeters cubed. 500 divided by 1,000 is 0.5. Now, if I rearrange the equation, because when I write out my equation, energy equals mass divided by volume, I can see that the mass is not the subject of the equation. I have to multiply both sides by the volume. So to get the mass, I'm going to do 0.5 decimeters cubed multiplied by 6 grams per decimeter cubed, and I'm going to get an answer of 3 grams. So at this point, I'd be leading up to talking about balancing equations, but this also brings us neatly to the conservation of mass law. And the question is, why do we balance equations? Well, let's think about our solute and solvent situation. If I have a solute which is 10 grams and I have a solvent which is 100 grams, what does my solution weigh? Well, the answer can't be anything other than 110 grams. I have 10 grams of solute, it's dissolved into 100 grams of the solvent. It doesn't just disappear, it's still there, it's still present. The solute is still in the solvent, but it's now mixed in a solution. So that mass still exists, it's still there. And this is the crux of the conservation of mass law. The mass of everything you start with must equal the mass of everything that you end with. So the mass of all of the reactants must equal the mass of all of the products. If you start with 110 grams, you have to end with 110 grams. If you start with 100 plus 10 grams, you can still end with 110 grams, but it never changes. It must be the same. Whatever happens at the start, you must end up with. And that is the conservation of mass law. The sign of a chemical reaction is that a new substance is formed. But note that we are not creating anything. In a chemical reaction, nothing is created nor destroyed. That's not possible. So the atoms and the elements that you start with must be the same as the atoms and elements that you end up with. The law of conservation of mass says everything you start with must be present when you've finished. The total mass of the reactants must be equal to the total mass of the products. And it also means when we're looking at balancing equations that the same elements that you started with must be present in your the same elements that you started with in the reactants must be the same elements that are in your product. If you start with 5 hydrogens, you cannot get rid of a hydrogen. You have to end with 5 hydrogens. So this is why balancing equations is important, which is why it's going to be a standalone video where I go through balancing equations. Okay, so the use of the conservation of mass law allows us to be able to calculate the masses of reactants and products from equations. Whenever you're given a question that says something like, how much oxygen is required to make 32 grams of water, you will be required to write a balanced symbol equation to start with. So you write your balanced equation, and you know that oxygen must have some hydrogen added to it to make water. So you work out how much hydrogen and how much oxygen you need, you balance that equation, and then you write down whatever masses you know. So you write down the mass of the water that you know. You work out the relative molecular mass or the relative formula mass for the things that you care about. Remember that chemical equations can be long and complicated, but you're only interested in the reactant and the product it's talking about in the question. I'll show you an example of this in a moment. But if they ask for oxygen and water, yes, you've had to put the hydrogen in the balanced symbol equation, but you don't need the mass of the hydrogen. You don't care about that. It's completely irrelevant for working out the mass. So we work out the relative molecular mass for those subjects. And then we calculate the moles of the known substances. Now, what are moles? That, again, I will tell you in another video, but essentially it tells you how many molecules there are in this reaction. Then you look at the ratio, and then you calculate the number of moles of the unknown thing using that ratio, and then you calculate the mass. Now, that sounds inordinately complicated, but I'll show you an example, and I'll make it make a little bit more sense. Okay, so as an example, we're going to look at this exam style question. If you're feeling brave and you think you understood what I've just said, pause the video now and see if you can work out this. At least have a go and see if you get stuck on any of the steps. Right, so if you have this question, how much chlorine do I need to make 53.4 grams of aluminium chloride? That seems oddly specific, right? 53.4 grams. There might be a reason for that. Let's have a look. So the first thing we do is we write out the equation. Not a balanced equation, just the equation. I know to make aluminium chloride, I'm going to need some chlorine and some aluminium, nothing else. So aluminium plus chlorine, which can only exist as a diatomic gas, Cl2, makes AlCl3. Now, you will normally be told this, or it will be a well-known molecule. You will not need to remember aluminium chloride is AlCl3. Okay? So, is this balanced? Well, I've got one aluminium on that side, and then I've got one aluminium on the product side. So my reactants, my products for aluminium are the same. Hooray! Brilliant. So I've got 2 chlorine in the reactants, 3 chlorine in the products. That's not good. Plus my product, well, it's an odd number, and I've got an even number on the other side. So the best thing to do to start with, first thing to try, is multiply it by 2. So if I look at AlCl3, multiply that by 2, so I've got 2 AlCl3. I've now got 6 chlorines. 6, hooray! But I've still only got 2 chlorines on the other side. Well, then I just take 3 of those. So I've got 3 Cl2s. I've actually got 6 chlorine atoms. So I've got 6 chlorine atoms on that side, 6 chlorine atoms on that side. Yes, we're on to a winner. But wait, because I've got 2 AlCl3, I've now got 2 aluminiums. I've broken the thing that was okay. But that's an easy fix. I just have 2 Als in the reactants. So it looks like this. 2 aluminiums plus 3 chlorine gas plus gives 2 aluminium chloride. Okay, so all we're trying to do is make sure you have exactly the same elements at the beginning and the end. Okay, so that mass is conserved. Conservation of mass. So what do we do now? You'll notice that I need to know how much chlorine I need to make 53.4 grams of aluminium chloride. So I don't actually care about the aluminium. I can just kind of skirt that off to the side. So now I need to know the relative molecular masses of the chlorine and the aluminium chloride. So that's what we do. To work out the chlorine, I need to work out the relative formula mass for 3Cl2. So that's 3, because it was 3 molecules, multiplied by 2 times 35.5. So that's 3 times 71, which gives me 213. So that's the relative molecular mass of 3Cl2. Do exactly the same thing for 2 AlCl3. Aluminium is 27. Chlorine is 35.5, multiply that by 3 because there's 3 of them, add them together, multiply the whole thing by 2, and I end up with 267. Great. So now I have the relative molecular mass for 2AlCl3 and 3Cl2. So I can say that actually, if I've got 213 grams of chlorine, I'm going to make 267 grams of aluminium chloride. And that's quite useful because now I can start to see how much one thing makes another thing. So what can I do from here? Well, I want to know now how much chlorine makes 1 gram of aluminium chloride. So I can just divide both sides by 267. So 213 divided by 267 grams of chlorine will make 267 divided by 267 grams, which is 1 gram of aluminium chloride. Perfect. So I've now got 0.798 grams of chlorine makes 1 gram of aluminium chloride. Fantastic. But I need 53.4 grams. So I just multiply that by 53.4 and I find out how much chlorine I need. So if it takes 0.798 grams of chlorine to make 1 gram of aluminium chloride, it takes 53.4 times 0.798 to make 53.4 grams of aluminium chloride. And that gives you 42.6 grams. So you need 42.6 grams of chlorine to make 53.4 grams of aluminium chloride. Okay, thanks for watching. So if you have any questions or comments, please do use the comments down below. I try to respond to all comments as quickly as possible. Please also give the like button just a quick little boop. That really does help the channel. It helps the algorithm know that people like this content and will ship it off to other people to come and watch. Watch out for the balancing equations video. That's going to drop in the next couple of days or so. All right, thank you very much. Stay safe and see you soon.